Our next type of sequence is geometric sequences. So geometric sequences are a sequence in which the next number or the next term can be found by multiplying the previous term by a constant factor. And the factor that we're multiplying by each time is the common ratio. So arithmetic sequences, we were interested in adding the common difference each time, whether it was positive or negative. But here, we're not adding anymore, we're multiplying, and we're not looking at the common difference, we're looking at the common ratio, which is R. So that's our difference with our geometric sequences. So how to calculate geometric sequences using recursion. And again, recursion's that step-by-step process where you find the first term and use that to find the second term. Then you use that to find the third term and so on. Same thing we have going on here. Our next term is equal to our previous term or our current term multiplied by our common ratio. Again, the factor by which it's growing or reducing each time. And here we have how to calculate our common ratio. So to find the common ratio, again, all we need to really do is solve by saying let n equal, because this will hold true for all of your numbers. But what we're saying here is the common ratio is equal to the next term divided by the previous term. And we'll illustrate that further shortly. So again, when we're calculating geometric sequences, the next term in the sequence is equal to the previous term multiplied by the common ratio. And you can also calculate that using a calculator. What you do is, again, you turn your calculator on, you enter your starting number, or T1, you press enter, then you enter your rule, which will be multiplied by, and then press equals to get term 2, equals to get the next term, and it'll continue on in that pattern. But again, that's a little bit painful, so what if we want to skip straight to a certain term number? This is where we use the nth term or the explicit definition. So Tn is equal to A, which remember, that's the same as T1, our starting point, multiplied by R, our common ratio, to the power of n take 1. Or, like we said, that's putting it into words. But another important thing to keep in mind is we actually don't cover logarithms in general maths. So solving this is actually probably more complicated than it might seem at first. So for geometric sequences, I find most of the time it's easier to use recursion. Or if it is like a bigger number and it is easier to use this formula, I definitely encourage you to use trial and error to find n. So that's actually a valid technique for solving these kind of questions. So if you've substituted in all of your values and you're trying to find n, then the best way to do it is say, let n equal 20. Oh, that's too low. That's not the answer I'm looking for. I'll try something again. Let n equal 30. Oh, no, I'm going to have to try again. So substitution and trial and error is actually completely valid if you're trying to solve for n. If you're trying to solve for Tn, it's a little bit more straightforward. But that's just like a brief overview of our geometric sequences. So again, here are our formulas. We have the next term is equal to the common ratio multiplied by like the current term or the previous term. And our R is equal to Tn plus 1 divided by Tn. And we can also use that to find the common ratio or also check if the sequence is geometric. So again, if we say, for example, if we said let n equal 2, then one way to find R is going to say R equals term 3 divided by term 2. And that'll give you R. Or if you say let n equal 5, it'll be term 6 divided by term 5. And because again, we're following a consistent predictable pattern and rule, the gap between each of our numbers is going to be consistent. So this rule, if it is a geometric sequence, will hold up for all of the gaps between all of your numbers. So example here, 2, 16, 18, 54. Is it geometric? Well, we can check that, but I can already see it's not arithmetic because I'm not adding a consistent number each time. So let's check it using our formula. What I'm going to say, like the example I gave before, I'm going to say let n equal 2. So by substituting every time we see an n in our formula, replacing it with 2, we can see that R is equal to T3 divided by T2. And term 3, 1, 2, 3, term 3 divided by term 2 is 18 divided by 6, which gives us 3. So that's our common ratio. And then to like properly check if it's geometric, we could check that the gap between these two is also consistent. And then that'll show us if we are following like a consistent pattern or rule. So here, for example, n, we're looking at terms 1, term 2, 3, 4, and 5. So here our rule, our starting point is 1, and our common ratio is 2. So we're multiplying by 2 each time. So doubling, 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 doubling. That's what's happening here in this geometric sequence. Here, I've added in an arithmetic sequence. So I've got t1 equals 1, and I've also got, so again, same starting point. They're both starting at 1, but this is multiplying by 2 every time, but this is adding 2 every time. So geometric, arithmetic. And I've color-coded them to hopefully make it a little bit more clearer. So again, you can see this is doubling every time. It's getting much bigger. This is just adding 2 every time. So those are our 2 different types of sequences. And we can actually graph them on the same graph to compare them. So this graph in blue, you can see this is our geometric sequence that's been graphed. You can kind of start to see it's forming like that exponential curve or pattern. So again, we're like multiplying every time. We're getting bigger by a certain factor, not just the same number. And again, our Tn depends on the term number. So again, that's just getting into like the formalities of why we graph n on this axis and Tn on this axis. As long as you remember to graph n on the bottom, that's awesome. That's all you need to make sure that you're doing. So let's graph our arithmetic sequence. Here, you can see I've placed my first red marker because term 1 in our first one is 1. Term 1 in our second one is also 1. Still the same. Our term 2 here is 3. Oh, so it's actually a little bit bigger than our other one here. But then let's see, our term 3 is 5. Still a little bit bigger. Our next term is equal to 7. Next one is equal to 9. So now all of a sudden, we can really start to see this pattern coming into play. And you can see here, I've graphed our, like, it's way off the graph, but I've graphed like our potential next term in our geometric sequences, term 6, 32, and this is our next term in our arithmetic sequence, 9, and then adding 2 to get to 11. So we've got 9 here, and then we add to 11. So you can start to see that they're fairly similar in the early stages here, but you can see that my geometric sequence is really getting like exponentially bigger. It's following that exponential curve, while our arithmetic sequences are going to follow that same linear trend forever if we keep our sequence going indefinitely. So you can start to see like just how different our arithmetic and our geometric sequences are, and when you graph that, you really start to see the pattern. So again, exponential growth is what we see in sequences, but we see that when r is greater than 1. That's when we see our exponential growth. For example, like a practical application of that is if we're modeling compound interest. The amount in our bank should hopefully be getting bigger by a certain factor of this amount, this r, each time the interest is applied. The other side of things is when r is less than 1, and we actually see like that exponential decay or depreciation. So with arithmetic sequences, if we have a positive common difference, we kind of like add 4, and if it's a negative, we might like take 5. To model the inverse of like exponential growth, we don't typically do like divide by this, although you totally could to model that. What we normally do is we still multiply it, but we multiply it by an r value that's less than 1. So for example, if I multiply it by 0.5, that's halving it. It's the exact same thing as dividing by 2, but we're just multiplying it by 0.5. So again, that's to illustrate that when r is less than 1, we'll see exponential decay. So for example, if something depreciates by 25% every year, it's becoming worth 75% of what it used to be worth. So our common ratio is 0.75. So whatever our amount is, We'll start at that amount and then we'll multiply it by 0.75 to model that it's depreciating by 25%. And then the year after, again, it'll decrease by a factor of 25%. So it's going to be decreasing, but again, it's going to be forming that exponential curve. So yeah, that's kind of in essence the difference between our exponential growth and our exponential decay. Last kind of thing I'll draw your attention to is the fact that exponential decay is again that like geometric sequence when r is less than 1. And, you know, we'll kind of start like it might start at this value and then it might lose 25%, lose. And it'll keep kind of, you know, losing that value but still making an exponential curve. But when we have straight line depreciation, that's modeled by arithmetic sequences because again, straight line depreciation is where we're losing the exact same amount each time period. So it might be like take 4 each period. Eventually we're going to reach 0. Whereas in geometric sequences or exponential decay, we technically actually don't ever reach 0 because it's just constantly being multiplied by 0.5. So it'll forever get smaller and smaller, but we'll never actually technically reach 0, which is interesting. And again, straight line depreciation is modeled by arithmetic sequences where the common difference is a negative number. So a geometric sequence example, a newly manufactured car is priced at $24,000. Each year, the car depreciates by 25%. Write a recurrence relation to model this scenario. And this is the answer that we have here. So again, this is a little bit similar in some ways to our cake scenario because n here is how much the car is depreciated or the car's depreciation after 1 year. But the newly manufactured car, when it's 0 years old, is 24,000. So that's really interesting. So T0, n is equal to 0. When 0 time has passed, it's worth 24,000. And we'd actually have to use our formula to calculate how much it would be worth after 1 year if we wanted to. And then our formula is, again, Tn plus 1 is equal to R, common ratio, 0.75, multiplied by Tn. And then that's the rough mark breakdown for that one. And then we could actually use this formula to calculate how much the car would be worth after 4 years. So, for example, T1, we're going to let n equal 0. So T0 plus 1, or down here, T0 plus 1 is equal to T1 is equal to 0.75 by T0. So that's the value of our brand new car. So what we're saying here, again, to break it down, after 1 year, so after 1 year has passed, our car is worth 75% of what it used to be. So that 75% times its original value gets us the next value of $18,000. Our car has dropped in value by $6,000 in a year. That's how much it's depreciated by. T2, same thing, except now we're doing, well, okay, after 2 years, it'll be worth 75% of what it was worth after 1 year. So we're going to do 75% times the value after 1 year, $13,500. Our car's dropped in value by $4,500. It's still dropping in value by 25%, but the amount that's dropping is less each time because it's a percentage, not a set number. Same for term 3 and same for term 4. And then asked in a sentence, answer in a sentence. Make sure you're getting all of those marks. So therefore, after 4 years, the car will be worth approximately $7,593.75.